Okay, I think I'm recording here. Hope everybody's having a nice snow day. And let's share my screen here. And hopefully you can see my PowerPoint here. Okay, last time we wrapped up the section or the first section of class on the largest physical scale of biomechanics, the whole body level, where we're primarily concerned with the motion and causes of motion in the center of mass, and introduced our last topic there, the energetics approach on whole body motion, and specifically the principle of conservation of mechanical energy and the transformation of kinetic energy to different types of potential energy and vice versa, while the total mechanical energy remains constant for a closed system. We left off there with our most complex example of conservation of mechanical energy, describing human motion, left incomplete. And this was the example with the gymnast on the balance beam and then dismounting the balance beam. I posted a link on the course website of a video of me walking through step by step, doing all the calculations for that problem. So make sure you check that one out. If you haven't already, it's in the most recent announcement that I posted on the course website. I'll add a caution here that this particular problem is probably the most complicated algebra type problem that we do in this class, both in terms of the total number of steps involved and in terms of just the difficulty of the calculations. And so if you think this is kind of hard, don't worry, it is hard. It's probably, at least from some perspective, the most difficult problem we do in this class. And if you get this one, if this one makes sense to you, that's a real good check on your kind of your overall understanding here, at least your ability to solve these types of, calculate this, calculate that problems. This is probably the most complicated one that we do. There's one a little bit later on that's maybe comparable, but this is certainly one of the two most complicated things that we do in this particular class. So again, I'll refer you to the video that I posted earlier for the specific details of doing this step by step. It's a fairly long problem. But let me just briefly orient you here and go through kind of the broad strokes of it in this video. So we have a 55 kilogram gymnast, and she dismounts from a balance beam. Dismount meaning she's on the balance beam, and then she jumps off the balance beam and ends up on the mat on the ground. And it says at the peak height of her jump, she's a certain distance above the ground. And when she's at that peak height, she has a certain linear velocity. She has a certain rotational velocity, so she's both translating and rotating here. And then she has a moment of inertia of a certain number there. And then we're asked four things. What's her total mechanical energy at her peak height? What's her velocity right before she hits the mat if she stopped rotating at that time? How much does the mat deform to bring her to rest if it has certain stiffness? And what's her average, or what's the average vertical ground reaction force applied to the mat if she is, brought to rest while landing on that mat there? So how do we actually do this? So keep in mind what's going on here. We have a gymnast who's on a balance beam, like you see in the figure here. She jumps off, and then we're asked to investigate what's happening here from the time of when she's at the peak height of her jump to when she lands and comes to rest on the mat. Okay. Now, for the first problem, or the first one here that asks, what's her total mechanical energy at the peak height of the jump? Generally, the first thing you want to do on these conservation of energy, total mechanical energy problems is you want to find some stage of this motion where you have everything you need to calculate the total mechanical energy. Okay, it all starts there because that's that conserved quantity, and everything else falls out of knowing what is this person's total mechanical energy at some point in this motion here. So let's look at our equation for total mechanical energy. It's the kinetic energy plus the potential energy plus the strain energy. Okay. And then if we parse that out into the specific formulas, there we can see what we actually need to input to be able to calculate numbers here. So I need a mass and a velocity. I need an angular mass, moment of inertia, and an angular velocity. I need gravity and height. And then I need stiffness and deformation. Okay. And then I go back to what do I know here? And I'm given all those things. I've got a mass, I've got a height, I've got a linear velocity, I've got an angular velocity, I've got a moment of inertia. Okay. In this first problem, she's airborne, she's flying through the air. So the gravitational acceleration, that's just going to be your 9.81 meters per second squared. You're airborne. There's no forces other than gravity being applied to you, so no appreciable strains or deformations on the body. So we don't need anything there for strain energy. But I have all the numbers I would need to plug in here to these other terms to calculate kinetic energy and potential energy. Okay, so plug in all those numbers, and you should get a total mechanical energy at the peak height of the jump of about 1,068 joules. Okay, so that would be our answer to this first question here. What's her total mechanical energy at the peak height of the jump? It'd be the sum of her kinetic energy due to linear velocity, her kinetic energy due to angular velocity, and her potential energy due to height above the ground. There'd be no strain energy here because she's airborne, no particular deformations happening here when it's just gravity acting on your center of mass. Okay, problem two, that's examining, if you can see me in my video here, let's assume that my glass of water here is the gymnast. So this is examining where she's at the peak height and then she falls from the peak down to the mat. Okay. And then the problem is asking right before she hits the mat, what is her velocity? Okay. Now, conceptually, what you want to think about happening there is I'm up here at my peak height and I've got a certain amount of total mechanical energy there. Okay. Some of it is kinetic energy and some of it is potential energy. Okay. As I fall to the ground, I'm still a closed system. The only force acting on me is that gravitational force, which is called a conservative force. It doesn't violate conservation of energy. So I'm falling to the ground. My total mechanical energy is staying the same. It's going to still be that total 1,068 joules that I calculated when I was at the peak height. So I'm at my peak height and I'm falling to the ground. And as I fall, because that's a closed system, the total mechanical energy is conserved and it stays at that 1,068 joules while I'm falling. That doesn't change. What does change is I'm falling from a high height down to a lower and lower height. And also gravity is acting on me and accelerating me and speeding me up. Okay. So my total mechanical energy is staying at 1,068. But as I fall, my potential energy is decreasing because height's decreasing, but my kinetic energy is increasing because my velocity is increasing. Now, there's a particular key to this problem that you need to recognize to be able to solve it. And it's a thing that's a common trick in word problems like this, where you're actually told a particular value of one of the terms in this equation without specifically being told that value. And let me explain what I'm talking about there. So this is a single algebraic equation here. And anytime you have one algebraic equation, you can solve for one and only one unknown thing in that equation. Okay? So this problem here asks us to calculate velocity, meaning if I'm looking at this equation right here, in order to solve that equation for this unknown linear velocity v here, I would have to know numerical values for every single other thing in here. Okay. Now I'm still airborne here. This is when I'm falling from the top down to the bottom, but I haven't hit the mat yet. I haven't slammed into the mat, haven't squished or deformed anything. I'm right above the mat. Okay. So still there's no forces acting on me other than gravity. There's about to be. I'm about to hit the mat, but I haven't quite hit it yet. So I can ignore strain energy. There's nothing going on there. Height, remember this is right before I've hit the mat. Okay. So even though the problem doesn't explicitly tell me height is zero, you have to then infer or assume from that that height is zero. Okay, I'm right before I hit the mat. My height is instantaneously zero right after I've hit it. Okay. So no strain energy, scribble that out, cross that out. No gravitational potential energy, cross that out. Still here though, I've got multiple things I don't know. Okay. I know my mass that was given to me. Velocity, I don't know, but I'm trying to calculate that. As I'm falling, my orientation of my body has probably changed, right? So I'd need a moment of inertia, but it didn't tell me that. And I'd have an angular velocity maybe, but it didn't tell me that, right? Now, go back to the problem though, and it says, what is her velocity right before she hits the mat? And here's the key part, if she has stopped rotating at that time. Okay? And that's the key description that you need to understand what that means physically and then translate that to your problem here. Okay. When it says has stopped rotating, that means you're not spinning, you're only translating. Meaning if you're not spinning, you're not rotating, your angular velocity is zero. Okay. So let's summarize here my different types of mechanical energy on the right-hand side. Right before I've hit the mat, I'm still airborne, so there's no appreciable strains in my body, so no strain energy. I'm right above the ground, height's essentially zero, so no gravitational potential energy. I've stopped rotating, so omega angular velocity is zero, so no rotational kinetic energy. So all I've got here that's left is my total mechanical energy equaling my kinetic energy right before I hit the mat. Okay. And remember, total mechanical energy is conserved. So the value of it here is still that 1,068 joules. And then that's equal to 1/2 times the mass of the gymnast, which is that 55 kilos from the start of the problem, times their velocity squared. Okay. So I know everything there as a numerical value except for that velocity. I can solve for that one thing, and I should get that right before they hit the mat, their linear velocity is 6.23 meters per second. Okay. So no strain, no gravitational potential, no rotational kinetic. All that I've got here is my total mechanical energy equaling my kinetic energy. I can solve for that velocity. Okay. Next one asks, how much did the mat deform as it's bringing her to rest? Okay. Now, what's happening here is this is the answer to the question of I'm falling, and at the top I've got a little bit of kinetic energy and a lot of potential energy. I fall, 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 and right before I hit the ground, I've got no potential energy and it's a whole bunch of kinetic energy. Then I slam into the mat and I stop. I come to a rest, and all that kinetic energy goes away. Where did it go? If my system stays just as the gymnast, then it looks like that energy was destroyed. It's gone. Okay, we can't destroy energy. It's not gone. What happened here is when I hit the mat, my system expanded to include not just me, but me and the mat. Okay. The other way you can think about this, if you don't like saying, oh, the system's bigger now, you can also think about it as you hit the mat, and the mat did work on you by applying forces to you to take that energy away. Okay, so either one of those perspectives is mechanically correct. You can say I hit the mat, and now me and the mat are one system combined, and the energy is transferring within there. Or you can think about it as it's still just me. I hit the mat applies an external non-gravitational force to me that does work on me and takes that energy away. Okay. So I hit the mat, I slam into the mat, and what's my situation there now that I've fallen from the top to the bottom and come to rest? Okay. Well, I came to rest, so there would be no linear velocity, no rotational velocity. So scribble out both of those terms. I've hit the ground, so I'm at a height of zero, so I would have no potential energy. But now I've hit the mat, right? Now I've hit the mat, I've squished the mat, and in the problem, I was given a stiffness, K, for the mat. Okay. So what's happened here is I slammed into the ground. All my potential and kinetic energy that I have is gone. Where did it go? Well, it got transferred into the mat as strain energy. Okay. So all that total mechanical energy, that 1,068 joules that I had before I hit the mat, that was all kinetic energy. Now I hit it, and it all got transferred into the mat as strain energy. Okay. So I would have 1,068 joules of total mechanical energy. And now it's all accounted for by strain energy stored in the mat. Okay. And I know this stiffness K. What I don't know is this deformation X. And in this problem, that's the only term I don't know. So I could algebraically solve for X and get that the mat deforms by about 6.5 centimeters. Okay. Now, this problem here, that would be assuming that between landing and hitting the mat, the only thing between your body and the mat that squishes and deforms is the mat itself. Okay. Which in reality is, of course, obviously not the case. You might think that this seems like kind of a big number, like 6.5 centimeters. That's like over 2 inches of deformation, almost 2.5 inches. That's a pretty large amount of deformation, even for like a squishy gymnastics mat. In reality here, there's other things deforming. Like the squishy parts on the bottom of the gymnast's feet are deforming by a little bit. If you land with like flexed, soft lower leg posture, like with your joints flexed and bending your hip and your ankle as you land, then your muscles around your joints are deforming and absorbing some of that energy. So probably the more general way to think about this is that it's not just the mat that's deforming, it's also the parts of the gymnast's joints and their body that's deforming as well and absorbing some of that kinetic energy as strain energy. Some of it goes into the mat, some of it goes into the body of the gymnast. So here in this problem, just to keep things kind of simple and straightforward, we were assuming it all goes into the mat, and you get this pretty large deformation from that. But in reality, some of it would go into the mat, yes. Some of it would go into your feet. If you're wearing shoes, some of it goes into your shoes. And then if you land with typical like good landing mechanics, some of it goes into your muscles as well. So what else goes into absorbing the energy? In this problem, we assumed it all went into the mat, but in reality, some of it goes into the deformable structures of your body as well. And that's why landing with good, like soft landing mechanics feels more comfortable than landing like straight, stip up and down, where it goes through bones and joint cartilage and stuff like that, which is typically not what we want. Okay, last problem here asks, or last part of this problem asks you to calculate the vertical ground reaction force acting on the gymnast as they came to rest on the mat. And that's going back to this idea of how do I change the total mechanical energy of a body? Well, I have to do work on it. And how much work? Well, enough work to remove the amount of energy that's being taken away or being added to it. Okay. So here, when I land, right before I hit the ground, I had 1,068 joules of total mechanical energy. And then I hit the ground, and the ground brings me to a rest and takes all that energy away. Okay. So if my total mechanical energy went down by 1,068 joules, that means that whatever is touching me, in this case the mat, had to do 1,068 joules of work on me. Okay. And remember, work is the force applied times the displacement or deformation that's happening. Okay. So F times X, and that equals my change in total mechanical energy, the amount of work that had to be done on me to change my energy. Okay. So the work done on me as I come to rest would be equal to that change in total mechanical energy, that 1,068 joules that the ground took from me. As it was taking it from me, we saw in the previous problem that it deformed itself by 0.065 meters or 6.5 centimeters. So here I know the work, W, it's equal to that 1,068 joules. I know the X deformation, it's that 0.065 meters. I can back out of there, W divided by X, the average force that's applied to me while the mat's bringing me to rest. And if you calculate that and do it right, you should get a force of about 16,000 newtons, which if you cast that in terms of the gymnast's body weight, that's 30 times body weight. Seems like a pretty large force, and that is a fairly large force. This is one of the reasons why gymnasts are pound for pound quite strong. They have large forces applied to the body. You have to be strong to do that and sustain that. Also, one of the reasons why gymnasts get quite a bit of injuries and lower body injuries specifically. They sustain quite large forces to the body when they're doing their landing activities. Okay, again, be sure you take a look at the video on YouTube, kind of walking you through step by step of doing those calculations. This will orient you to kind of the broad strokes of stepping yourself through that. But the more detailed video that I posted the link for takes you on a more step by step approach of doing those specific calculations in a software like Excel. Okay, so we are actually done now with the first largest scale of biomechanics in the class. Remember, we're going from larger and larger to smaller and smaller physical scales of biomechanics as we proceed through the semester here. So we started at the whole body level. And at the whole body level, we talked a lot about movement of the body that involves interacting with our environment to move the body around from place to place. Now, that interaction with the environment necessarily involves, for activities like walking or running, contacting the body with the ground and using our limbs, our lower legs, in particular ways. Okay? And so that's the next physical scale of biomechanics that we will investigate, the limb level, and specifically using our lower bodies in different ways to interact with the ground to move the whole body around. Now, there's of course multiple limbs of the body. We typically call them the arms and the legs. Most people with fully intact bodies have two arms, a left and a right, and two legs, a left and a right. Arm and leg are actually anatomical terms that specifically mean like arm is specifically what you might generally refer to as a forearm. And I'm not flexible enough to show you my leg here at my table, but leg is specifically like the lower leg or the shank, the part of the limb between the knee and the ankle. And so you'll typically, if you want to be strictly anatomically correct and refer to the whole length, the whole thing, like the whole arm from shoulder to fingertips, or the whole leg from hip to toes, the upper body one would be the upper limb, and the lower body one would be the lower limb, if you want to just broadly refer to like the whole thing. Limbs are our primarily means of interacting with the world. I use my upper limb to operate the keyboard and grab things and manipulate things or put my glasses on. I use my lower limb to contact the ground with my feet and generate forces that support me against gravity and transport me from place to place. So the limbs are our primary means of interacting with the world to do things, broadly speaking. Here, because of the importance of locomotion for moving around, and just because of my expertise primarily being in the lower limb, we'll mostly talk about the lower limb. But a lot of what we talk about here would apply in mechanically similar ways to using the upper limb as well. So a video here that we've seen before, but here is an example of an athlete using their lower limb to interact with the environment. So notice here as they press their feet into the ground. So watch right as his foot hits the ground here, you'll see these traces of these forces under his feet fluctuate and change. Okay. The big dotted line here is the force in the vertical direction, and the smaller solid line is the force in the horizontal, the anterior posterior direction. So you can see as he hits the ground, he generates a large vertical force to support himself against gravity and generates first a negative or anteriorly directed horizontal force that slows you down a little bit, followed by a positive or posteriorly directed horizontal force to speed himself back up a little bit. So this vertical force, that's a force generated by our limb contacting the ground to support our whole body against gravity. And these horizontal forces, that's forces that are going to end up accelerating us in different directions, either forwards or backwards as we move across the ground. Okay? So generating forces with our limb contacting the ground that affect the motion of our center of mass at that larger physical scale. Now, you'll notice here, let me back up to the video, that as this person is running, that they're doing this repetitive cyclical motion. It's step, 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 step. Humans in general want to cover with our locomotion distances that are relatively long compared to the size of our bodies. Like I'm 6 feet tall, my legs are roughly 3 feet long, but when I get up and move around, I typically want to cover much longer distances than those distances than I could appreciably do with like one, discrete movement of my body, right? We typically want to travel hundreds of feet, maybe thousands of feet at a time, right? And because we can only go a particular fairly short finite distance with one discrete motion of our bodies, we have to do these cyclical repetitive motions to travel distances that are appreciably longer than the rough size of our body, right? So like if I wanted to get up from my table and go to my car outdoors, which is about 100 feet away, I wouldn't be able to do that in like one tremendously powerful jump, right? I don't have that accuracy. I'd have to stop and open the door along the way, and it would be a very effortful thing to do, even if I didn't have to do those things. It's a lot easier to take just repeated steps or repeated cycles of shorter distances that all add up to that longer distance. Okay. So we do these repetitive cyclical motions to do activities like walking and running to travel distances that are much larger than the dimensions of the body itself. Okay. So let's get some terms down for describing that cyclical motion. Okay. Generally speaking, we describe the cycle of gait or the cycle of locomotion, whether it's walking or running or sprinting or whatever, as events that are occurring within a stride or within a gait cycle. Now, this is easier to see than to just hear me talk about it. So, as this video starts, I'll try to pause it where it's actually happening. This athlete's right foot is going to touch the ground at some particular time. So right about there is when his right foot has first touched the ground. Okay. So there's nothing magical about that first instance of like when the right foot or the left foot or whatever foot, the first instance of part of the foot touching the ground. There's nothing magical, mechanical about that time. We just use that as kind of a convenient convention for calling that's the start of the gait cycle. Okay, so right here, this person's starting a gait cycle. That cycle proceeds until the next time that you see that same event again. So the right foot hit the ground, they keep going, left foot hits the ground, they keep going, and then I'll stop it here right around when their right foot hits the ground again. Right about there. Okay. So everything that you saw in motion there from the right foot first hitting the ground once until that same foot, the right foot hitting that ground again, that would be one full gait cycle or one full stride. Okay. Everything that happens temporally and mechanically between two consecutive instances of the same gait cycle event. Okay. And again, there's nothing magical about having that event be heel strike or touchdown or whatever of the right foot. That's just a convenient place to start it. So that like in biomechanics, when we all use the term gait cycle, we're all speaking the same language. It's two consecutive events of the same event, and typically we define that event as like the initial contact with the ground of the right foot, or sometimes the left foot. It's not particularly critical left or right, but two consecutive initial contact events of either foot, or one foot or the other, either the right foot or the left foot. Okay. So that's a stride, two consecutive cycle events. For example, right heel strike to the next right heel strike. Now, if I play that video again, you'll notice here their right foot contacts the ground. And then about halfway through that stride, their left foot hits the ground right there. Okay. So that's about halfway through. I do right and then left and then right. Most people, healthy, able-bodied people have roughly symmetric bodies, and so that's roughly halfway through. We move roughly symmetrically between the left and the right parts of the gait cycle. But you can think of that kind of halfway point, so right and then left and then right again, that halfway point between the right touchdown and the left touchdown, that's kind of half of a gait cycle or half of a stride, and we call that a step. Okay. So that would be, for example, between when the right foot strikes the ground until when the left foot strikes the ground. Okay. Then to complete the cycle, there'd be another step after that between when the left foot strikes the ground and then the right foot strikes the ground again. Okay. So within each stride, there's two steps. One starting with contact of one foot, and the other starting with contact of the other foot on the other side. Okay? So stride, full cycle, step, half a cycle, two steps in each stride, a right step and a left step. Or if you're starting the other way around, a left step and a right step. The order is not particularly important. Now, the total amount of time that it takes to do that whole stride, that would be your stride time. You could also have a step time if you're just looking at a step, usually be roughly half the stride time, not necessarily strictly half, but roughly half. Now, also notice within each cycle here, like if I'm looking at the right leg, there's a portion of that stride where that limb is in contact with the ground. And then starting right about here, a portion of the stride where that limb is not in contact with the ground, where then it's airborne. I'm swinging it through the air here until it hits the ground again, right about there. And then I'm doing another contact phase. Okay. And then I push off and do another airborne phase right there. Okay. Now, that fraction of time, either within a stride or in a step, whatever you're interested in, where the foot's on the ground, we call that the contact time, how long the foot is positioned on the ground. The other part, where you're airborne, we call that typically the swing phase. Okay, so there's a contact phase, the part of the gait cycle when that leg is on the ground, and there's a swing phase, the part of the gait cycle where the leg is airborne and being swung through the air. Okay, so stride, whole cycle, step, half a cycle, stride time, how long the whole thing takes, contact time, how much of that time is spent with your foot on the ground, and then swing phase, the part of how much of it is not with the foot on the ground, how much time you're airborne. Now, all those descriptors would apply equally in a conceptual sense to our two main motions of locomotion, walking and running. As humans, we're capable of lots of different types of locomotion. We can hop, we can crawl, we can skip. But as adults, under normal circumstances, we generally only use two modes of locomotion. We walk when we're taking things easy and don't really want to get anywhere fast, and we run when speed's more important and we want to get somewhere fast. Okay? Now, both walking and running involve cyclical strides made up of two steps each, periods of time where the foot is on the ground, period of times where the foot is airborne for both the left and for the right leg. But there's some kind of fundamental differences here between walking and running. Okay, so broadly speaking, they're similar in that they all involve strides, they all involve intermittent contact with the ground, they all involve this cyclical motion. But there's some fundamental differences between how we use the legs and how the legs mechanically behave in interacting with the ground that results in fundamentally different mechanical energetics and patterns of motion of the center of mass of the body. So notice here in walking on the top and running on the bottom. In walking, here in the kind of pinkish line that's traced out there, you can see in walking as you move along, doing strides, the center of mass is kind of bobbing up and down cyclically as you translate yourself. And also in running here, you see kind of a similar thing, tracing out the path of the center of mass there in that orangish line, where it's bobbing up and down as I perform strides and translate myself. So some conceptual similarities there. But notice here, both of these pictures of these gait cycles are starting at heel strike of the right leg, or at initial contact with the ground of the right leg. But notice as I proceed through that contact phase, the pattern of motion of the center of mass is fundamentally different between walking and running. In walking, I hit the ground with my right leg there, and my center of mass first initially goes up and then starts going back down as I proceed through that contact phase. In running, it's the opposite thing. In running, I hit the ground with my foot, and instead of going up like it did in walking, my center of mass initially goes down, and then as I proceed through that contact phase, it goes up. Okay? So some fundamental differences there, right? Walking, I contact the ground, my center of mass vaults up and then down. Running, the opposite. My foot hits the ground, and I go into the ground, and then push up off the ground. Right? So some similarities at the kind of spatiotemporal scale of just broadly what's going on here. Yeah, I hit the ground, I contact the ground, then I come off the ground. But some differences in these two main modes of locomotion in the pattern or the sequence of motion of the center mass that results from that ground contact. Walking up and then down, running down and then up. And just showing that closer here, more zoomed in, I touch the ground and walking on the top and running on the bottom. And walking, I immediately go up and then down. And running, I go down and then up. Now, those different patterns of motion, as we just talked about, height being associated with potential energy and the speed of motion being associated with kinetic energy, you might imagine if the gait for walking is sending the center of mass up and then down, and the gait for running is sending it down and then up, there might be some differences in the patterns of the fluctuations of their kinetic and potential energy in between those two gaits, and there indeed is. Here we see in each of these four rows here, the blue line is always showing your kinetic energy of your center of mass as a function of time here over that stride cycle of walking. Okay? Or over that stride cycle of walking or running. The orange line, similarly, is showing your potential energy due to gravity of the center of mass as a function of time over the cycle of that mode of locomotion, whether it's walking or running. The top two panels here are showing kinetic in blue and potential energy in orange of the center of mass for a stride of walking. The bottom two, with again kinetic energy in blue and potential energy in red, are showing the energy of the center of mass for running, for a stride cycle of running. Okay? Now, what you should pay attention to here, what you should pay attention to here is look at the relative timing, just in like a gross sense, like rough directions here, of how the kinetic energy and the potential energy fluctuate while you're doing these two movements. Notice in walking, as the blue line, the kinetic energy goes down, the orange line, the potential energy is going up. Okay. And then similarly, as the blue line, the kinetic energy is going up, the potential energy is going down. Okay. We call that anti-phase fluctuations. Okay. As one goes up, the other goes down. Okay. Such that if you were to add up this blue line and this orange line, one's going up, one's going down, others going up, others going down, you'd get a relatively flat line as the sum of them, right? One goes up by 50, one goes down by 50, you sum that and you get a relatively constant level of the sum of these two types of mechanical energy. Okay. For running, we see the opposite, right? Generally speaking, as the blue line kinetic is going down, the orange line's also going down. Then as the blue line's going up, the orange line, the potential is also going up. Okay. So those aren't anti-phase fluctuations, those are in-phase fluctuations. They're both going up and down at around the same time. Okay. And if you summed those up together, you wouldn't get a constant sum of those two. You get a fluctuating sum of those two. Okay. So that goes back to our notion of conservation of energy, right? It looks like in walking, energy is conserved, right? Similar to how we talked about, you drop the eraser and it starts with all potential and then gradually transforms into kinetic, but the sum stays the same, right? Looks like in walking, that's kind of similar to what's going on. As kinetic goes up, potential goes down, and vice versa, such that the sum of them is relatively constant. But then running, it looks like it's violated, right? Kinetic went up and potential went up, so my total mechanical energy is fluctuating, right? So it looks like I'm violating conservation of energy. I'm not. I just haven't accounted for all the different types of total mechanical energy. Remember, there's a third type of interesting total mechanical energy, that strain energy, that is relatively large in running in the leg, but relatively small in walking in the leg. And then if I include that in the running, then I get a picture of conservation of mechanical energy. So that elastic strain energy, that's kind of the key energetic difference between the mechanical behavior of the leg in walking and running. In running, you hit the ground and your leg kind of compresses as you're, accepting your body weight on the ground, and then it decompresses or kind of springs off the ground as you push off the ground and get airborne and get ready to hit the ground with your next leg. Right? So you have this compression of the leg storing strain energy in the leg, or transferring gravitational potential and kinetic energy into the leg as you hit the ground, and then releasing that, springing off the ground to get more potential energy, more kinetic energy as you boost yourself off the ground to get ready for another gait cycle. That's happening appreciably in running, but not so much in walking, at least not as much of a big factor in walking. In walking, we keep the leg relatively stiff and relatively straight, and we kind of vault over that leg and let gravity pull us down towards the ground as we do the next step, rather than actively pushing ourselves off the ground with that leg as we do in running. Now, there's some fairly simple models we can use to biomechanically explain those observations. We'll detail each of these in greater detail in the lectures that follow this. So I'm just kind of briefly introduce them today. But we can think of walking as a inverted pendulum, a mass stuck to the ground that kind of bobs back and forth on a relatively stiff, relatively straight leg. Okay. To move efficiently with a relatively stiff, relatively straight leg like that, we take advantage of gravity, converting naturally kinetic to potential energy and vice versa, and generating some momentum for us. And the key parameter there, and this is one of the reasons why like tall people tend to walk faster than short people, is the leg length. For running, we're not so much an inverted pendulum on a relatively straight leg that just bobs back and forth over the ground. We're springy, we're bouncy. We bounce along the ground on a compliant, springy, bouncy leg. Okay, we're more like a mass attached to a spring-like leg that bounces along the ground on that spring. Okay, so we, rather than using gravity and momentum for efficient motion, we use storage and return of elastic strain energy in the leg for efficiency of motion. And the key parameter in that particular mode of locomotion, from this like simple, dynamics perspective, would be the stiffness of that spring, governing how much energy gets stuffed into that spring for a given deformation. Now, you can come up with a variety of simple and not so simple models to kind of describe the leg here, with these spring-like actuators and muscles and tendons acting as springs and stuff like that. So lots of various different levels of detail here you could use to describe like how the leg behaves in locomotion in general or in walking versus running specifically. Um, Regardless of the complexity of the model that you're using or of the mode of the goal or the mode of locomotion, the goal of locomotion is always kind of the same, whether you're walking or running, right? I want to translate the center of mass and I want to do it at a certain speed. Okay. And speed, remember what is speed? Well, mechanically, it's the rate of change in position versus time. But in biomechanics, as we saw in your first lab exercise, lab two, in biomechanics, speed is, yes, rate of change in position versus time, but it's also a function of my stride mechanics, my stride length times my stride frequency. Right? Now, at any particular speed that I want to travel at, I will naturally use some particular combination of stride length and stride frequency, right? But I don't have to do that, right? If I want to travel at a speed of 10, I could use a stride length of square root of 10 and a stride frequency of square root of 10, right? If I want to travel at a speed of 4, I could use a stride length of 4 and a stride frequency of 4, right? But I'm not restricted to that, right? There's infinitely many different combinations of stride length and stride frequency that would all multiply together and give me a speed of 4, right? I could do it with my normal steps. I could do it with short little choppy steps. I could do it with big, long, slow steps. But if I just tell you to go out and walk, you would normally just use some modest combination there, right? You wouldn't naturally use short little choppy steps to walk at that speed, and you wouldn't naturally use big, long, slow steps to walk at that speed. You'd use your normal steps. Now, similarly, as people increase their speed, like if you go from a slow walk to a fast walk, or from a slow jog to a max sprint, you will do that with some particular combination at each one of those speeds of stride length and stride frequency, ultimately giving you whatever particular speed at. And as you increase your speed, you first tend to do it by, in the solid line here, taking longer and longer strides. Eventually, you get to like your longest possible or longest comfortable stride. And if you want to get faster and faster, so you've maxed out stride length there, if you want to get faster and faster, you got to increase stride frequency, which is this dashed line here. Right? But at any one of these speeds, accepting this like maximum possible speed here where I can't, possibly go any faster or change much, at any particular slower speed, to go at that speed, there's lots of different combinations of stride length and stride frequency that I could feasibly mechanically use to travel at that speed. Again, I could use short little choppy steps, I could use big long slow steps, or I could use something in the middle. But in all those cases, I could use those different combinations to all meet that broad goal of traveling at the same speed. Okay. So what's magical about that kind of subconsciously preferred uh, combination of stride length and stride frequency that I use to say walk at my normal comfortable speed? These are some older data here. These are data from like the 1950s from individuals walking on a treadmill at a set speed. So the speed was used to set you at a particular speed. And then they had them walk at a variety of different speeds, either faster or slower speeds than their particular preferred speed. And they measured how much metabolic energy, how many calories they used to walk a mile at those different speeds. And they got this interesting U-shaped relationship here, where there's some moderate speed in the middle, where the energy that it takes you, the calories that you burn to travel a mile at that speed is minimized. Okay? At faster speeds, you were less economical. It cost you more calories per mile to travel a mile at that faster speed. And at slower speeds, you were a less economical walker. It cost you more calories per mile to travel at that particular speed. Okay? Now, that had been observed before. The cool thing that this Ralston 1958 study is famous for is they noted that the speed at which your calories per mile is minimized for most people is really, really close to your natural speed, the speed that you would naturally walk at if I just asked you to walk and didn't give you any particular special instructions or you're not under any particular time constraints. Right? So kind of giving a biomechanical slash physiological energetic basis to the psychological concept of having a preferred normal, quote unquote, normal speed that you like to walk at. Maybe the reason you like to walk at that speed, whether you know it or not, is because we're kind of inherently lazy, right? We don't want this common easy, normal thing to be hard. So we naturally do it in a way that is mechanically and energetically the easiest way to cover that distance. Now, similarly, like I said, you can walk or run at any particular speed with a variety of different combinations of stride length and stride frequency. But if I just tell you, just walk at any given speed or run at any given speed, you will use some specific combination of stride length and stride frequency to do that, right? And why do you do that? Well, it also seems to have an energetic basis, right? Here's a similar study where they had an individual or lots of individuals walking on a treadmill at a set fixed speed, but then they used a metronome, to impose different step rates on the person so that they would say, okay, take shorter, quicker steps to walk at that speed, or take longer, bigger, slower steps to walk at that speed. And then at all of those different combinations of step length, step rate to stay at that same speed, they measured their energy expenditure, how many calories they burned to walk a mile using a short little choppy step length or a big long slow step length or lots of things in between. Okay. Again, they found this characteristic U-shaped relationship where there's some rate of steps or stride rate or cadence, whatever you want to think it as, in the middle that minimizes energy cost of walking. If you take shorter, choppier steps, energy cost went up. If you took longer, slower steps, energy cost went up. And again, interesting thing they saw here is that the combination in the middle that had the minimum energy cost of walking is very, very near for most people your natural preferred step rate, like the step rate that you would normally subconsciously use with no particular instructions if I tell you just walk at that speed, or if I put you on the treadmill and have you walk there, but don't like constrain your step rate anyway, just the one that you would naturally use. So there seems to be a kind of a connection here between the psychology, the preference of moving in a certain way and the energetics and the mechanics, the energy that it takes to move in that way. Humans are kind of inherently lazy. We like to naturally do things in ways that are conservative in terms of how much energy it costs us to do these things. Now, we'll eventually see, and that's it for today. We'll eventually see that this concept of energy, whether it's mechanical energy or metabolic energy, is key to understanding how our legs interact with the ground and how we move in these simple ways using the leg as kind of a rigid pendulum that we bob along with in walking versus a springy leg that we bounce along with in running. Very closely connected to the mechanical energy, which is very closely connected to the metabolic energy, which is the quantity that the human nervous system seems to care about a lot and seems to want to keep that kind of subconsciously low when we don't have to force it to be high. When we have the option of moving in a preferred way, we seem to move in ways that minimize how much mechanical energy it takes to move in that way. Okay, that is it for today, and we will see you next time.